if you agree.
Okay, so then welcome to the afternoon session, and I'm happy to introduce Gesualdo Delfino, who will speak about exact results for quenched randomness and criticality.
Thank you very much. It's a real pleasure to be here for the final week of this workshop. Thank you, the organizers from. So my topic today is quenched disorder, which quite obviously fits two of the keywords of the title of the workshop, because it deals with random variables and universality classes of critical behavior. Until recently, however, it would have not fitted the third keyword, integrability, because exact results for critical behavior in disordered systems in 2 dimensions were never found in spite of long investigations. So the purpose of the talk is to show you that actually now we have exact access to this special type of critical behavior. So the talk is on paper, some of which with Elena Tartaglia when she was postdoc in Trieste, and others with Noel Lamsen, who was my PhD student. And they are reviewed in this last paper in a compact way. So first of all, what is, let me remind you, by quenched disorder? Now, quite often, statistical systems a fraction of their degrees of freedom, which take too long to reach thermal equilibrium with respect to any reasonable experimental scale. So what one does is to take these degrees of freedom out of the thermal average in the partition function and to treat them instead as random variables on which one averages at the level of the free energy with some probability distribution. Here I'm collectively denoting by J this random degrees of freedom. Examples of this arise in magnet, this spin glasses, and others. Now, the starting point, the main fact, if you want, is that experiments and numerical studies show that these quenched disorder systems are able to play new specific classes of critical behavior, that they are different from the ones you get in the pure system. In this context, pure systems mean the system without disorder, okay? So these new critical points are often called random critical point for short. Now, from the point of view of the theory, the problem has been not extremely difficult. Let me say once forever that everything I say corresponds to short case interaction, which is the main case we are interested in. There have been perturbative results in this, because one of the difficulties of the problem is that it is hard to find perturbative limits. Weak disorder. Otherwise, the problem has been studied numerically. So this has been mainly a field of numerical study. Oh. Okay, let's try. Okay, so I was saying the study of this problem has been mainly in view of theoretical difficulties. And a very striking feature has been the total absence of exact results in 2 dimensions. This is striking compared with the case of the pure systems, where essentially all the universality classes were solved already in the 80s, in particular exploiting the power of 2-dimensional conformal symmetry. Even more striking is this point if you think that it has been rigorously known since the 80s that in 2 dimensions, disorder softens first-order transitions into second-order ones. So the second-order ones are in which the correlation length diverges, which display conformal invariants. And then this means that in the disorder case, there should be more room for conformal invariance than in the pure case. Still, the conformal field theories for these critical points with disorder were never found. Now, to move a step further into this problem, I will refer to the Potts model, which received attention over the years, just because it's a model which displays the main features of the problem of quenched disorder. So I remind you that the model is defined on a lattice where at each side you have let's try this. No, I'm left. Yeah, there are at each side, there are these, there is a variable which takes Q values, and it is useful to think of them as Q different colors. Then the interaction is a Kronecker delta here in the Hamiltonian. It just distinguishes whether nearest neighbors have the same color or different color. And then the invariance of the Hamiltonian is that under the global permutation of the colors. It is well known that there is also a cluster formulation of this model which allows to take Q as a continuous variable, not integer, and this is what I'm going to do from now on. Now, in this Hamiltonian, these bond couplings Jij are eventually the random couplings, but the pure case without disorder is a particular case in which all these couplings take a single value J. If J is positive, this is a ferromagnet. And for the pure ferromagnet, no disorder, has been known since a long time that the transition is a second order up to Q equals 4, then becomes the first order beyond that point. So this is precisely a case in which the result of Eisenman and Ware tells us that in this order case, there should be instead the second order transition line, which goes up to Q equal infinity. And it is also expected that this line will end at Q equal 2 in the pure model. Q equal 2 is the easy model. The reason is that in this limit here, disorder becomes weakly relevant from the renormalization group point of view. And this is the condition in which you can find a perturbative critical point. So this line was extensively investigated numerically in the early 90s. Yes.
If J is considered the pure ferromagnet one that we put out.
Yeah.
So why there's a phase condition? Because there's only one term. There's no competing term.
No, the phase transition comes from the spontaneous breaking of this symmetry.
So it's with respect to temperature.
Yeah, well, it's the usual story. So Q equal 2 is the easy model, if you think for a moment, is the usual story. So these numerical studies found indeed these properties, these 2 points for this line, but found also something more apparently, because within their numerical accuracy, these studies pointed to a possible Q independence of the critical exponents along this line. Of course, this is surprising because Q is the symmetry parameter, and universality tells us that the exponents should depend precisely on the symmetry. So in the pure systems, you never have this kind of symmetry independence. So this was intriguing. A name was also introduced, the name of super universality. This idea, however, didn't last for long, actually, because in 1997, Cardi Jacobsen, always numerically using the transfer matrix, clearly showed that the exponent beta, the magnetization, is Q dependent. And for new correlation length exponent, they concluded for a weak dependence. So this was the, I would say, it is fair to say, the last main development, and nothing substantially new happened in the following 20 years. So recently I looked to this problem and I realized that we can have an exact access to these random critical points in 2 dimensions. And I will tell you how this goes. So this is done within, so this is relies on an idea of years before, or looking at criticality in 2 dimensions within a scattering formalism. So when we are close to criticality, the theory can be described by Euclidean field theory with 2 space dimensions, which, however, as always, is corresponds to the continuation to imaginary time of a relativistic quantum field theory in 1 space and 1 time dimension. In this quantum version, we have particles, which are correspond to the collective excitation modes of the system. And from these particles, we can build a scattering theory, which encodes the interaction properties. Now, the theory is relativistic. This means that if 2 particles scatter, any number of particles can be produced in general, in a general relativistic theory in the final state. At the level of the analytic structure of the amplitude, this means that there will be infinitely many branch points, branch cuts, with branch points starting at increasing values of the energy, and this is the center of mass energy squared, this variable S, and all these branch points, their location is proportional to m squared. So in general, this is a problem if you want to do to use this framework at criticality, because at criticality the correlation length is infinite and the mass is 0. And then you have the collapse. If you set the mass to 0, infinitely many branch points collapsing on top of each other. So this problem is essentially intractable. But the point is that for what I want to do, this catastrophe doesn't happen, because we are in 1+1 dimensions. I expect conformal symmetry, which now has infinitely many generators. They will provide infinite quantities that need to be conserved during the scattering. And this, if I start with 2 particles, will forbid all the processes in which I produce more than 2 particles. So I'm left only with the elastic scattering, and which means just 1 cut and no catastrophe. Once you understand this, we can go on and play the game. This is my pictorial representation of the scattering amplitude for a 2-body collision. The amplitudes carry also, the particles carry an index A, B, C, D, because they can come in several species. And so I will use this notation for such a scattering process. In two dimensions, there is only a single relativistic invariant, which is the center of mass energy. This is dimensionful, of course, is an energy. And since at criticality we have scale invariants in particular, these amplitudes cannot depend on the energy. So they are just constant. These are enormous simplifications of the scattering problem in such a way that the general constraints coming from unitarity and crossing of any relativistic scattering theory take this particularly simple form. Okay, unitarity is conservation of probability, and crossing gives a relation between the direct channel of the scattering and the cross channel. Okay, so these are the rules of the game in general. At this point, we can show how this works with the model. It turns out that the ON model is simpler than the Potts model, slightly simpler. So for illustration purposes, it is convenient to start from that. So the ON model, you have at each side of the lattice an n component unit vector with this scalar product interaction among the nearest neighbors. Now we want to do the scattering framework. Let's start for simplicity, of course, from the pure case. So the Jij are all equal. Now the first thing to do is to inject in the general picture the information that we are dealing with the ON universality class. And this is done taking a basis of particles which carry a representation of the ON symmetry. So this is a vector multiplet labeled by an index A going from 1 to n. And then when two particles collide, this is a state from the ON point of view is a rank 2 tensor. And the requirement of that the scattering preserves the ON symmetry is that you have to see in how many ways you can contract the indices here at the 4 terminals. And there are 3 ways: either annihilation and then production of a new pair, either transmission or reflection. Once you have the amplitude, we just we specialize the crossing and unitary equations that I wrote before in general form to this case. So crossing says that S1 in the cross channel is like S3 in the direct channel. You have this relation. It's convenient to introduce parameterization in terms of a modulus and a phase. S2 instead is real. I call it rho 2. Then the unitarity equations take this form. And at this point, by construction, the solutions of these equations are the critical points of pure systems with ON symmetry. If you want, in the RG language, the renormalization group fixed points with ON symmetry. Okay, the solutions of these equations are listed in this table and shown also here in this figure in a subspace of the scattering parameters and as a function of n. So n is on this axis. There are essentially 3 solutions. The first one is characterized by the fact that only the transmission amplitude is non-zero. And it is plus or minus 1 by unitarity. So these are just free bosons here up here or free Fermits down here. The second one exists for n between -2 and 2. And anyone familiar with the ON model in 2 dimensions here recognizes the critical line of the gas of self-avoiding loops, which is precisely defined here. The self-avoiding condition also appears in the solution because you see there is this rho 2, which is 0, but rho 2 was S2. So the crossing is 0, you are just left with the self-avoiding vertices. So there are two branches one knows from the lattice for this gas, the dense branch, the dilute regime, and here you also find the two branches. The third solution has two peculiarities. It exists only at n equal 2, and it has a free parameter. So it's not just a single critical point at n equal 2, but a line of critical points, which is this line here. And this, of course, is the line of critical points which accounts for the Berezinski-Korsterlitz-Taules phase in the XY model. Okay, so we got these critical lines in the pure case are already known, but a feature that emerges of this approach is the ability to give this information all at once. Normally, these things are studied separately. Here, you get everything at once, and you see how the different pieces talk to each other. And now we can go and play the same thing in the disordered case. So this will be the new case. This was the warm-up. For the disordered case, we have to remember that essentially most of what we do theoretically relies on the replica trick. We have to average over disordered the free energy, which is the log of the partition function. And mathematically, the log can be written in this way. So this is just a mathematical identity, but it has the interesting feature that maps the disorder into a source of interaction between n replicas of the same system. And dealing with interaction is what we like in physics, right? And so we are going to exploit precisely this also within the scattering approach. So we always, this is for ON always, but with disorder. So we go in this replicated system. So in each replica, we have a vector multiplet. So this is why I add now this index I, which labels the replicas. Little n is the number of replicas. And now we write the amplitudes for these replicated systems. We have the first three amplitudes where all the excitations of the particles are in the same replica, just one replica I. So this is very much the same as in the pure case. But then we have three remaining amplitudes in which couple different replicas. So replica I with replica J. Then we write again, as usual, the crossing symmetry and unitarity equations, which take now this form. So you may notice that in these unitarity equations, both capital N, the number of vector components, and little n, the number of replicas, enter as parameters that do not need to be integers, which means that in particular, we can take straightforwardly the limit of little n equals 0, which is essential for the replica trick. Okay, so everything is here encoded, and the solutions of these equations with n equals 0 are the critical points of with ON symmetry and quenched disorder. This is the list of solutions. Well, I have to say maybe one more thing about this parameter ρ4 here. You see, when ρ4 is 0, these two amplitudes S4, S6 are 0. S5, due to this relation, becomes plus or minus 1, which is the free case. So ρ equals 0 is the case of zero disorder, in which the replicas are decoupled. So ρ4 plays the role of disorder stent. Okay, Rho 4 equals 0, there is no disorder. Rho 4 small, there is small disorder. So this is why the first three solutions of Rho 4 equals 0 are those of the pure case. But then you have these additional solutions. This V1 has a varying disorder, which vanishes at n equal 1. N equal 1 is the easy model. While the other two are always strongly disordered. There is no weak disorder limit. Okay, here I'm plotting these solutions. This is in this plane of complex plane of the amplitude S4. So Rho 4 is the modulus of this amplitude, which means that in the middle of this plane, you are in the pure case. And when you move radially outwards, the disorder increases. And this is a projection. This is just a cartoon. It's not quantitative, but so it's a qualitative projection on a plane in which you have n number of components here and the disorder strength on the vertical axis. Now we know, I'm also putting these arrows here to illustrate the direction of renormalization group flow among these critical lines that one can argue. First of all, knowing that in the pure system, the disorder will be, weak disorder will be relevant below this in point, n equal 1, while it becomes irrelevant above. This is why at n equal 1, you have this perturbative limit. You see, there is the disordered green line, which ends in the pure case. But this green line also has an endpoint here at the value n star that from our solution takes this value. And this compares reasonably well with the numerical estimate obtained by these authors some years ago. Then this green line here join this strong disorder solution S1. For n equal 1, this point here is known in this model. It goes under the name of Nishimori point. So this line is kind of generalization of these Nishimori points to generic M. And then there is a last line of strong disorder, which is where the flow, RG flow, ends at 0 temperature. Okay, so this is the ON case. And now we can move to the Potts model, which actually was the first one that I solved. But this is slightly more complicated, so it's better to, it is easier to discuss now. So the Hamiltonian is this. Let's look at the scattering picture for the pure case, first of all. So we have to take a basis of particles which implements the symmetry, which now is permutational symmetry of Q colors. This is done. Think of this line here as the space-time trajectory of the particle. Then you interpret the particle thinking that the trajectory separates space-time in two regions characterized by different colors, alpha and beta. So when you go to a scattering amplitude, there are 4 regions that you have 2 colors. And there are only 4 possibilities which are inequivalent under permutations of the colors. So either the 4 colors are all different, or 2 of them are equal in this direction, or in this direction, or in both directions. So some of you may be familiar with this from the work of Cimez-Zamolodchikov for the pure ferromagnet, where the particles are kinks interpolating between different ground states, which are degenerate in the ferromagnetic regime. Here we are at criticality, so there are no degenerate ground states, it's just a single ground state, there are no kinks, but still we can use this as a general way of implementing the permutational symmetry of the colors. So again, once we have the amplitudes, we can write down the crossing equations and the unitarity equations. Now the space of solutions of these unitarity equations will be the critical points of the pure Potts model in 2 dimensions, and the solutions are in this table. Well, first of all, you see immediately this solution 3, which ends at q = 4. And you recognize here the critical line for the pure ferromagnet, which we said already is known to end at q = 4. On the other hand, there are other solutions. And this is a case in which, at variance with the ON case, already in the pure model, the scattering method gives some information that was not known before. For example, you see that the maximal value for which the solutions exist, and for which then a second order phase transition is possible with the permutational symmetry of Q colors, is this number, which is about 5.5. So this is larger than what one usually expects on historical grounds. So historically, only solutions existing up to Q = 4 were known. So this leaves the possibility of a Q = 5 second order transition for the Potts model, which however should occur in some antiferromagnet. Because for ferromagnets, all lattices give the same result because of universality. But for antiferromagnets, the lattice structure is important and in principle should be investigated by case by case. So there are a priori infinitely many possibilities. Some of them have been studied, there have been some proposals, then revisited. The problem of finding a lattice with the Q = 5 transition is still open. On the other hand, this first solution has the peculiarity of existing all at Q = 3. It has a free parameter, so it's a line of critical points. And soon after our result here, a lattice realization was found by these authors, again in antiferromagnetic interaction, and this for quadrangulations of a spatial types F2. Okay, skip this, and now we move to the disordered case. So the strategy is the one we already saw for ON. We have the particles as before, but now they exist in each replica, and there is this additional index I labeling the replicas. And then we write the amplitudes. The first 4 only have excitation in the same replica I. And so they are as in the pure case. But there are now 3 additional amplitudes which couple different replicas, I and J. And again, rho 4, for exactly the same reason we saw for ON, plays the role of disorder strength. These are the unitarity equations. Now the full list of solutions of these equations is quite long, so I will not try to write it down. I will discuss some main points of things which happen in this space of solutions. So first of all, I'm directly in the limit of zero replica, which is relevant for the disordered case. The first thing that you find is that there exists and is unique a solution which exists for any q up to infinity and ends in the pure model a q equal to in this point. So this is precisely the line of critical points in the disordered model that was studied numerically since the 90s. And it is seen here analytically and actually exactly for the first time. And for the first time, you see this phenomenon of softening of the first order transition that you have here in the pure model into second order one. And the solution is written here. And well, you see clearly that it depends on Q. But now there is something interesting which occurs, because you have this solution, but you can look at it in different symmetry sectors. Because you can go in the sector in which the two colliding particles form a state which is a singlet under the permutations of the covers. And then you can isolate the amplitude for the scattering in this singlet sector. And wow, okay. I'm showing in this figure this amplitude for the singlet sector as a function of Q on this axis, but also here I'm showing it before taking the limit and going to zero. So there is also n, the number of replicas on this axis. Now you see that as long as n is not zero, this amplitude depends on Q. But when you go to n equals zero, which is the limit you have to take for quenched disorder, this amplitude becomes a constant, no longer depends on Q. And this is something that never happens in pure systems. So this means that as soon as we have, for the first time, the ability to look at an exact solution for this problem, we see this form of superuniversality actually emerging from the solution. And then this is consistent with a Q independence of the order of the correlation length critical exponent nu, because nu depends only on the scaling dimension of the energy density, which belongs to the singlet sector, is invariant under permutations of the color. On the other hand, the beta, and for this exponent nu, numerical studies never found appreciable deviations from these in value, and this even for large Q. On the other hand, the magnetization exponent beta, which is known to certainly to be Q dependent, doesn't belong to this singlet sector. If you go in the sector corresponding to beta in this solution, the Q dependence there remains. Okay, so this is about this line, but in the model there are also other critical lines. This can be understood if you look at this phase diagram obtained from numerical simulations. This is for Q equal 3. And this is in the plane of temperature and disorder strength. And so there is a ferromagnetic phase, magnetic phase, and a phase boundary. And along this boundary, there are fixed points of the renormalization groups, which are precisely the points I'm finding. So at zero disorder here, we have the transition of the pure system, which corresponds at Q equal 3 to this point here. Then when you increase disorder, switch on disorder, you get this fixed point, which is the one I just discussed on this line. But then when you go on, there are two other fixed points which have the property that are always strongly disordered. There is no weak disorder limit for this fixed point as a function of Q. And indeed, in the space of solution, you find these solutions which are always strongly disordered. Now, here I'm plotting against just a single parameter of 4, and you see just a line, a single line. But if you look in the more generally within the parameter space, you will see that this is not just one solution, but there is more than one. So both of these are covered. Then another interesting point, well, let me discuss first here. Well, you see, the renormalization group pattern is that when you start from the pure model, here weak disorder is relevant. And so it drives you from this pure critical point to this disorder critical point, which is infrared stable. On the other hand, this line should be infrared stable and is infrared stable from numerical studies up to Q equal infinity. But then from the renormalization group point of view, you ask, what is the starting point of the flow for Q larger than 4, which should end on this line? Because for Q larger than 4, in the pure model, there is no criticality. So this suggests that in the space of solution of the disordered system, there should be a solution which starts precisely here and then moves at largest values of Q. And this line should provide the starting point of the flow for Q larger than 4. And if you look in the space of solution, this solution is there. It's this orange line I'm showing here. Okay, so I think I'm more or less in time, and I can conclude just saying that somehow, very surprisingly, after so many years, we realized that random criticality in 2 dimensions can be accessed exactly. And the approach only relies on symmetry, so it works for any disorder strength. It gives all the critical points. A striking feature is that when you look at this problem now, the exact solutions, you find these symmetry independent sectors, which in this sense are super universal and appear to be characteristic of this type of criticality. So in the pure case, there isn't nothing like this. And of course, the last main point for the future is to understand whether we can take advantage of what we learn from the scattering approach and move on also on the identification of the conformal field theories describing these random critical points from the point of view of traditional conformal field theory in terms of Virasoro algebra. Okay, with this, I stop. Thank you.
Thank you very much. So there's time for questions now.
Sorry, in the introduction, you said that there were results that did not agree with super universality. But
yes.
Now, this last line, yes?
Yes. So Karden Jacobsen found that the exponent beta but for nu, their convergence, it is everything is numerical also in Karden and Jacobsen. So their numerical convergence for nu was not as good as for beta. So they saw that nu was not very much. They had not enough numerical accuracy to make a very precise statement. They just concluded that there should be some weak dependence, but still some dependence. Now, this point remained open up to now from the point of so in numerics, you always have some error bars, but nowadays they are quite small. And as I was saying at the end, still now, the value of nu as a function of q remains compatible with nu equal 1 within error bars. The point is that previously, there was no reason to imagine about a theoretical mechanism that could split the fate exponents with respect to the q dependence. So one expects, okay, if beta depends on q, also nu will depend on q, just a weak dependence. But now from the exact solution, you see that in the exact solution, there is a superuniversality at the level of the scattering amplitude. And so this is a partial superuniversality because it occurs only in some symmetry sector. So this is only in the singlet sector. The singlet sector is the sector on nu. So this is consistent with the nu, which is actually q independent, while beta, if you go in the sector of beta in this solution, there is a q dependence. So this is a mechanism which allows for superuniversality of some exponents. Okay, some.
May I ask another question? But how do you know that the theory is, once you do the scattering theory, how do you know the theory is conformally invariant?
This is another interesting point. Conformal invariance has been my main assumption, actually. So I started this, for the pure system, we know that there is conformal invariance. But for the disordered systems, historically, there has been no analytic evidence of conformal invariance. There have been a couple of papers providing numerical evidence. What they did was to take some specific critical points, I think at 0 temperature, looking at some boundaries of clusters and checking whether numerically they were compatible with some SLE structure. Okay, and these tests were positive. So I should mention these are papers by Ledussal, Santachiara, one of them, and with some co-author that probably I'm forgetting, I'm sorry, I apologize, and also Martin Weigel, another for another group of authors. So there was only this numerical evidence.
But I mean, in your method, how do, in the S matrix approach, how do
my
you know?
method is built in. I start, my method starts here. It is because there is conformal invariance and infinitely many generators that I suppress all the inelastic processes.
For
so
the form of the answers you use for the bootstrap.
Yes, so it's not an answer. If you say, I look for conformal invariant points, it's not even an answer. You're looking for conformal invariant points. Now, the point is that the fact that everything I find is consistent and explains actually what was found numerically over the years means that we have here for the first time serious theoretical evidence that all these critical points with disorder are conformal invariants.
And how do you know that the system is indeed unitary?
Is?
Unitary.
No, it's not unitary. There is no unitarity here. Remember that when you go to the disordered case, you do the replica trick. So here you lose any unitarity.
But you impose unitary on the S matrix.
They are different unitarities. Okay. The S matrix, the unitarity of the S matrix is just the conservation of the probability. So in the scattering, the sum of the probabilities, all the events has to be 1. But this has nothing to do with what you call unitarity in conformal field theory.
Okay. Thank you.
Since you just put up the slide, I mean, you know, this is the replica method, and I mean, some people wonder whether, you know, this gives the right result. I mean, you have any comments on that? I mean, you know, it's sort of always a little bit debated. I mean, also for spin glasses, and I just wonder whether you have any comments on the validity of the replica method.
Well, I'm not in the context of the analysis of spin glasses, which is done, you know, that is done for the mean field version of the problem that eventually will hold in infinite dimensions. Okay, so here I'm doing something more direct. I'm infinite dimension, more precisely 2 dimensions, and this replica method has been normally used to, in particular, to do the perturbation theory in situations, like here, in this weak disorder limit, and has never really been in question in this context. So I use it quite safely. And the fact that the results match support seriously the replica method.
Okay, are there other questions? No, I have a question on what features of the disorder would you expect the central charge to depend on? I mean, is there anything you can say about it?
Well, here the central charge is a delicate story. Depends what we mean about.
Well, if you think of the conformal field theory, you would.
Yeah, in the conformal, strictly speaking, so I should go. You see, the point is that in the replica setting, you take these n replicas. And so each replica will have a central charge, but when you take n going to 0, so formally this central charge goes to 0.
Okay, I see, that would be.
So the peculiarity, one reason, actually the main reason, we should argue, for which these conformal field theories have not been found with traditional methods, is that you have to work in a space of central charge equals 0, which is very difficult to characterize because in itself means nothing. Everything is hidden in the limit. Okay, so you need a way to perform this limit in a controllable way. So this is one way, which is exact.
I see, right, yeah. Okay. The other, yeah.
Once you know the S matrix, you could do the form factor expansion and discover that there are signs of the conformal field theory is non-unitary, or some effects of that the theory is non-unitary, or you cannot.
Well, non-unitary in the conformal sense. I mean,
yes. You cannot work the form factor if it is a conformal theory.
I mean, the problem of form factor here comes before. The problem here is you have massless particles.
Yes.
And the power of the form factor expansion in general is that it converges very fastly in the massive case. It's a large distance expansion. As long as the mass is finite, it converges very rapidly. But here the mass is 0. And so you lose this property, and it doesn't look up to now a viable approach, but maybe some new idea can come. So it's not at all straightforward.
Okay, so if there are no further questions, then let's thank the speaker again.
Thank you.